Here are solutions to homework set number 6 for ECE 463-663 Modern Control. This homework set looks at pole placement, finding a feedback control law to stabilize the system using pole placement techniques. Now the first problem looks at a cart and pendulum system. So here's a cart. It's got a beam 1.5 meters long, a mass 3 kilograms at the tip. Apply a force at the base to keep it balanced. Back from homework set number 4, the dynamics, linearized about vertical, is as follows. Come up with a feedback control law of the form full state feedback such that the settling time is 5 seconds. You've got 5% overshoot for step input. So, starting out, and once you're done, check the step response in MATLAB, check the step response in the nonlinear system. So, starting out, I've got to translate the requirements to pole location. 5 second settling time means the real part of the dominant pole is at minus 0.8. 5% overshoot tells the damping ratio, telling you here's your dominant pole. So what I want to do is place the dominant pole at minus 0.8 plus minus j.83, its complex conjugate, and fourth order system, so put the two other poles somewhere out of harm's way. Kind of arbitrary where you put them. I chose minus 4, minus 5. If I do that in MATLAB, here's your A matrix, B matrix, using pole placement. Here's your feedback gains. This one is kind of large, so it might be a bit of an issue, but we'll try it. Checking, I checked the closed loop eigenvalues. They're right where I put them, so pole placement was working. Now set the DC gain to 1. Find the DC gain to the position, the first state. Add KR to make the DC gain 1. So here's your control law. There's KR, here's KX, and this is how you calculate U. Next, let's check the linearized system. If I take the closed loop A matrix, A minus BKX, closed loop B matrix, BKR, C and D, take the step response out to 8 seconds, here's what you get. So I get this undershoot. I don't like that, but this is how the system behaves. The settling time is about 5 seconds. I've got about 5% overshoot. DC gain is 1. Looks good. Now the acid test is try that on the nonlinear system. So on the nonlinear system, here's my feedback gain KX, KR. I'll make the set point go from 1 to 0 for step input. Let's try that again. And let it run for 15 seconds. So here I'm going from 0 to 1, step to the right, step back to the origin. This is a nonlinear system with the dynamics found from homework set number 4. Here's the feedback control law. Plot it, plot the outputs, and you get that response. This undershoot I don't like, but you're kind of stuck with it. Physically, the way the system behaves, to get it to go right, I first have to go left to get it to move, to lean. To get it to go left, I first have to go right to get it to start leaning left, then catch itself. The nonlinear system has a bunch of sines and cosines in the dynamics. Apparently the lean isn't enough to really cause trouble. What that tells you is I can actually make the system quite a bit faster. I'm not really pushing the design in this case. But there, I destabilize it. As a kind of a test, just to show it really does work. At 13 seconds, I'll turn off the input. So everything's fine. For 13 seconds, I've got the feedback control law. Then when I turn off the control law, it falls. So the feedback control law really was doing something. Okay, problem number 2. Repeat for ball and beam system. So here's the linearized dynamics at 1 meter, back from homework set number 4. Find a feedback control law to meet these requirements. So same procedure as before. For a different A matrix, different B matrix, find KX to place the poles. So for this system, here's the feedback gains. And checking the closed loop poles right where I put them. That seems good. Pick KR to make the DC gain 1. So here's your control law. There's KX, here's KR. For the linear system, take the step response to the linearized system. That's the closed loop A matrix is A minus BKX. B matrix is BKR. Take the step response. Looks reasonable. Again, got 5% overshoot. DC gains 1. Settling time is about 5 seconds. Nonlinear simulation. Let's go back over here. Go to the ball and beam system. I apply the feedback gain KX, KR, calculate it, and simulate the system. So here, tell it to go from 0 to 1. The ball starts rolling to the right. Beam goes up to catch itself. A little bit of overshoot. Again, I designed for 5% overshoot. Comes back. Tell it to come back to the origin. Beam goes up, comes down to try to catch itself, get a little bit overshoot, and then comes back and stops at the origin we're supposed to. So again, the feedback gains actually do work. Last problem. For a double pendulum, control this puppy. So back from homework set number, well, one homework set. Back from the lecture notes, here's the dynamics of the double pendulum. Using full state feedback, I want to get the similar response. So what I do is, once again, here's a closed loop or open loop A matrix, open loop B matrix, place the poles. Here's the dominant poles. The other 4 poles, put them someplace out of harm's way. I chose minus 4, 5, 6, and 7. Not really sure where else to put them. Checking it should behave the way I expect. The eigenvalues of the closed loop system are right where I put them. Pick KR to make the DC gain 1. Now when I simulate the linearized response, I get just what I expected. For the nonlinear system, go to a double pendulum. Here's my feedback gains, KR, KX. When I run that one, I go over from 0 to 1. A little bit of overshoot. Get a design for 5% overshoot. Going from 1 back to 0. 1 to minus 1. It's done a good job controlling it without causing a lot of swinging. And the step response, again, is just about what I expected from the nonlinear simulation. The angles aren't getting that excessive, so the linearized model is fairly accurate. What that also means is that I could push the system. I'm not really pushing it that hard. I could make it faster. That is homework set number 6 for modern control, using full state feedback to control a system.